All right, then we're ready here in Big Sky, Montana. Welcome everybody. I am here with our panelists. We have Abel Méndez, Irena, Mamajanov, Timothy Lyon, Justin Filiberto, and Kennda Lynch. And I am the MC for the night, Edgard Rivera-Valentín from the LPI. We are coming to you live from the First Billion Years Habitability Conference. We just wrapped up the conference, and we're going to review some of the science that was discussed here with our panelists. But before we begin, I thought it'd be good to do an introduction of each of our panelists and their expertise. So starting over with Justin, if you can please say your name, affiliation, your degrees, and your general area of study.
Hi, I'm Justin Filiberto from the Lunar and Planetary Institute. I have a PhD in geology. I'm a petrologist, which means I study how rocks form. So pulling them apart based on minerals and chemistry to put it together. I forgot the third thing I'm supposed to say, but I think it was what I presented. So what I've been looking at is a Mars analog site on the Colorado Plateau where lava came into interaction with sulfur-rich sediments and remobilized them, producing a habitable environment.
Hi, everybody. I'm Kennda Lynch. I'm also a staff scientist at the LPI with Justin and Ed. Degrees. Gosh, I'm an odd duck. So I have a PhD in environmental engineering and also degrees in aerospace engineering and biology. I started out my career first as a systems engineer and turned scientist, so I'm kind of a little bit of an odd duck. In general, though, I am a geobiologist / astrobiologist these days, and I study extreme environments here on Earth to understand how life interacts with these environments, how they live in it, how they survive in it, how they're preserved in it, so that we can look for signs of life in similar environments on other planets.
Good evening. I am Irena Mamajanov. I am currently a principal investigator at ELSI, Earth Life Science Institute, which is part of Tokyo Institute of Technology. My degrees are all in chemistry. I have masters in organic and PhD in physical. But for the last 10 years or so, I've been studying prebiotic chemistry, and my main question is to explain how life could have arisen on our planet or anywhere else in the universe.
My name is Abel Méndez. I am professor of physics astrobiology at the University of Puerto Rico, Arecibo. I direct the Planetary Habitability Laboratory. My name is Abel Méndez. I am a professor of physics and astrobiology at the University of Puerto Rico at Arecibo. I am also the director of the Planetary Habitability Laboratory right there. My specialty is planetary science and biophysics. I work with how to combine ecological models to explain the possibility of life in exoplanets. My main focus is in planetary habitability, and hablo español.
My name is Tim Lyons, although I really like the Lyon. It sounds a lot more exotic. I'm Irish, not French. I'm a professor of biogeochemistry at the University of California, Riverside. I'm also the director of the Alternative Earth Astrobiology Center there, and the team lead of one of the NASA Astrobiology Institute CAN 7 groups. My specialty, my history is first training in geological engineering, and then in geology, and for my PhD in biogeochemistry. As a PhD student, I studied the modern ocean, but always with an eye of developing tools for understanding Earth's history. And so I've spent the past few decades actually exploring the history of Earth, our environments as they've evolved at the surface, and the coevolution of life, with a particular focus on oxygen in the atmosphere and the ocean. and how that has been driven, those changes by life, and how those changes have caused evolution of life. And through NASA funding in recent years, I've been, as part of a large team, been steering our understandings of Earth evolution and specifically evolving atmospheres to try and guide the search for life in biosignature gases on exoplanets.
All right, so the way we're gonna work this is I have two general questions for each of our panelists. They'll each take about 2 minutes to answer that question to introduce you all to the type of science that was discussed here at the conference. And then we'll open it up to a Q&A. So if you actually would like, you can start typing in your questions, and then I'll start reading through them when we get to the Q&A section. So to begin, the first question I'd like each panelist to answer is, what is one takeaway you have from this conference?
So one takeaway I have from this conference is where we're investigating for the origin of life. Most of the textbooks still either have us looking at soup on the surface of the Earth or deep sea vents. And the big thing from this conference is wet-dry cycle. So an environment that was wet, then dried out, and then became wet again, being vital for origin of life.
One takeaway I have from this is just kind of a little bit more fundamental in how much we really need cross-communication between the planetary folks and the biochemistry and chemistry folks to discuss this whole issue of origin of life. We're both attacking this problem from different ends, but it's the same problem, and I think we can attack it better if we're talking together. So that was the biggest takeaway, is that we really need to do more integrated work with our planetary people, working with our biochemists and our organic chemists to really start hitting this issue hard.
I think coming from this conference with appreciation of how difficult, how complex, and how nuanced the field of origin of life and the field of habitability is. And I'm actually I'm coming out of this conference appreciating even more how nuanced, complex the questions of habitability and the questions of life's emergence on Earth or elsewhere are. And I'm looking forward to more discussions like this and to future collaboration with scientists in other different fields to really tackle and try to assemble this whole complex tapestry that is habitability and life.
My takeaway from this conference is that red dwarf stars might not be that bad for habitable planets. It is primarily believed that these stars are very active during the earliest stage, and they produce probably enough radiation to blow off the atmosphere of their planet, even that they eventually end in the habitable zone. But planets might recover the atmosphere during time, and so it seems that these stars are not that bad as previously thought.
I think my takeaway is something that I might have predicted. Generally, when we go to conferences, we tend to go to ones that are very specialized, and they're often meeting with the same people and having the same arguments or the same sort of mutual backpatting. And so what I've really appreciated about this meeting is that I've met a lot of new people, and that the range of questions asked and expertise brought to bear on those questions is really broad. And so I've learned a lot, and in particular about sort of the commonality of the things that we know and that we wish we knew, and the different approaches that we can each use to go after those questions.
All right, thank you very much, panelists. The next question I have for you is, what is something you learned during the conference, specifically something that surprised you? Not just your takeaway, what was weird. I know Abel already mentioned he thought M-dwarfs were going to be completely uninhabitable, right? And suddenly he was taught a lesson that they might actually be, planets around M-dwarfs might actually be habitable. So what is something you all learned from this conference?
I always knew that life managed to find a way to live in extreme environments, but it wasn't until this conference till I realized how extreme life, or how extreme environments life can still survive, down to the most acidic environment to the most alkaline waters, high temperatures, low temperatures. Life on Earth finds a way to live there.
I learned, this kind of surprising, I learned about the fact that, to really think more about false negatives. I mean, and I think this is something that Tim brought up, this whole concept of we spend time on false positive, making sure that something that we think look like life, but isn't, and making sure we understand what those false positives are. But I realized when Tim was talking about this that I really don't think about false negatives at all. And he's right. It's very important for us to, understand where we might have a false negative, where there could be elements of life there, but we think that they're not, because we could basically just miss the needle in the haystack because we don't think it's life. And I realized how much I don't think about that. And I'm looking forward to thinking about that a lot more in my work.
So I think that's one thing I started thinking here, and I haven't thought of it before. So in our field, conditions for origin of life and conditions for habitability are usually used interchangeably. And just in one of the talk here, I think it was really conceptualized for me that conditions for origins and only a small subset of habitability, and this is something we need to take into account when we're thinking about life on other planets and mechanism of how it might have developed.
I saw three environments. Last Sunday, we had a tour through the Yellowstone Park, and that was amazing. I was able to see different kind of street environments, very acid environments, and water at high temperature with a lot of microbial life going. I come from the tropics where everything is habitable, so it's very good to see something quite different from what I used to.
So for much of what I do, it's really sort of tracing the nutrients in the ocean through time, and those are principally, we have lots of carbon around, so principally the limiting nutrients are phosphorus and nitrogen, and trace metals that play really important roles in catalyzing reactions and enzymes. And so I tend to think for nitrogen in particular that it's really a life story, and it's about life that can fix the N2 that abounds in our atmosphere and make it into a form that's more biologically available for a much wider swath of organisms. And so one of the things that I've maybe refined my thinking about from this meeting is the importance of abiotic processes, the degree to which in the absence of life you can produce essential ingredients that, that life can use. The last part I said is that how important abiotic processes, in other words, things like lightning and other things, photochemistry, that occur in the complete absence of life, that generate ingredients that are essential for life. And I think my community has tended to be a bit dismissive about that in a quantitative sense. We knew it occurred, but perhaps it's more important than we imagined.
All right, thank you very much. And just a note for our conference attendees, because we are on the hotel Wi-Fi, sometimes the audio will cut out. So when that happens, I'll ask our panelists to restate what they said while the audio was cut out. All right, so that was the introductory questions that I had, and now I'm going to go to the chat and go through the questions that we've been receiving. Again, please type any questions you have on the origins of life, habitability, and the search for life beyond Earth in the chat, and I will ask them to our panel. So the first question that we have is from Craig. Craig says, what is the current status of organic molecules, i.e. amino acids, fatty acids, nucleotides, sugars, etc., in carbonaceous chondrites, just as the Murchison CM2 in the origins of life?
So yes, we do know that there are organic molecules in most meteorites, especially the carbonaceous chondrites, but they've actually been found even in Martians and some of the other meteorites as well. Those are probably delivery mechanisms for bringing organic material to the Earth early in its history, but we don't have evidence for life in any of them.
All right, thank you. I hope I answered the question. So we have another question, and luckily enough though, we do have the Associate Director of the LPI here with us as well, Dr. Alan Treeman. And this might be an appropriate question for the administration at the LPI, and that is, Brian Wade asks, I have a general question about the conference. This is the final meeting of this conference series, where there'll be a follow-up on conferences. Will there be follow-on conferences related to this series? Alan?
Hi there, this is Alan Treeman. Thank you for the question. One of the things the LPI has to do as part of its contract with NASA is to produce series of conferences like this called initiatives. And in this, what you've heard now is the last of the 4 conferences in our initiative of the first billion years. And we will be doing additional initiatives over the next couple of years. We haven't actually formally set up one, decided on one yet, but the idea that's most relevant here is actually one of Edgard's, which is about brines in the solar system, which of course relates to habitability in terms of the hypersaline organisms, there's presumably brines on Mars, brines on Enceladus, the ocean on Europa may very well be briny. So that's our idea at the moment. That hasn't been set in stone, but we would like to continue with the successes we've had here.
All right, thank you very much, Alan Truman. All right, so next question is, in the media, today we learned an exoplanet orbiting its star in the habitable zone. So someone would like to give us more information about that discovery. How habitable is habitable? Here with us, we do have Abel Méndez, who is an exoplanet astronomer. So Abel Méndez.
Today was announcing that the one planet that we know for many years now, the planet is called K218b. It's a planet around a red dwarf star, 100 light years away. So it's pretty far compared to other known planets. So for the first time, we have the detection and the atmosphere and even water vapor in the atmosphere of this planet. We have done that before for a few large planets, but this is the smallest planet that we have the detection of the atmosphere, and the planet is also in the habitable zone. This doesn't mean that the planet could be habitable, because based on their size, is still much larger than Earth, about 2 times or even more. So probably the composition of this planet is like a mini version of our planet Neptune. That means mostly composed of gas. There's other alternative. It might be an ocean planet. But even if it's an ocean planet, it doesn't mean that it has a surface with liquid water, because at that size, we also have a strong, dense atmosphere, and the pressure will make any water solid, even that it has the right temperature. So anyway, this is a stream planet. In any case, it could be habitable for microbial life, but still, that's a long stretch.
Thank you, Abel. All right, so now this one, I think each one of you will have your own opinion on this, so please definitely, each one of you answer this. Other than Earth, which planetary body in our solar system do you think is most habitable? Most today, in the past, it's this one. I'm gonna leave the temporal component up to each one of you.
Okay, so Kennda Lynch from LPI. So there's two sides to that question. There's the, current habitability, what is the most habitable right now in modern time, versus what was the most habitable probably, in literally the first billion years. In my opinion, and I'm biased because I study Mars, I think that in that first billion years, I think that Mars was potentially one of our most habitable planets because it was very Earth-like, an Earth-like atmosphere. We had liquid water on the surface. We had a lot of ingredients for life potentially there on Mars. So I think that the likelihood for Mars to have an origin and propagation of life was pretty good in the first billion years. For habitability today, I'm running with Enceladus, because I think, with those with the tiger claw vents and all the extreme energy that we have down there, and knowing that we have a lot of salt constituents in the water, I think that there's all the pieces are there again for life to arise. And we've got chemical disequilibrium going on so that we can have, so that life can take advantage and gain energy. So yeah, I'm going with Enceladus, but I've just learned a little bit more about Ceres, and so it's kind of a close second for me for current habitability today.
All right, I will follow on with what Kennda said, and second, Mars being the most habitable, at least early in its history. And there was some discussion at this meeting whether or not Mars was even more habitable than the Earth early in its history. So 4-point-something billion years ago. For today, I'll take Europa over Enceladus. It's a bit larger. I think the ocean and the interaction between the ocean and whatever rocky crust is underneath it will be a great place for potentially life to take hold.
This is Tim Lyons. I don't want to echo too much what has already been said, but I'm a Marsophile, as everyone is here as well. But for me, and this is completely a bias, I think the signatures of life on early Mars are a challenge, and it's a challenge worth undertaking. But I've learned from the early Earth how difficult how elusive it can be to find those things. I get really excited about both Europa and Enceladus. Europa has a wonderful redox juxtaposition because of the high flux of radiation from Jupiter. There's lots of oxidized material. There are ice dynamic models where you can envision those oxidized species being brought into a reduced ocean, and that's what life is. It's about that flow of electrons. So that's really exciting. The discovery of hydrogen in Enceladus, the plumes, the ability to fly through those with some certainty and sample materials within them, it's a hard call for me to pick between those two. And it's, I think, there's a very reasonable expectation that we'll find something exciting in both those places.
I can't say much about necessarily habitability. I don't necessarily can comment on habitability, but I would be very excited to study Titan. So there's evidence for a lot of organic chemistry going on here. And if Titan has life, the life would be very different from the life we have on Earth. And if we could detect it, it would be the most exciting discovery, in my opinion.
This is Abel, seeing all my friends here talk about the solar system. I'll talk about exoplanets. And the issue here is that we know about maybe 50% planets that we might consider potentially habitable. That means that they have some requirements for what we know for life, but we have very limited information about them. So, so there is a competition between who will be the first to detect extraterrestrial life. Even the solar system, you have the planets are accessible by exploration missions, but for exoplanets, we are limited to remote sensing. We have to observe from afar, and from that limited information, try to decide if those planets are habitable or not. But that's something interesting that we are exploring.
So the question started as within the solar system, but I want to go on the record as saying that I'm really, in my heart, an exoplanet fan as well. And so we know of over 4,000 of those planets now, and that's extraordinary to me. And my friends tell me that probably every star has planets around it. It's a natural consequence of star formation. And so when you think about that and the quality of the discoveries that we're making already and the potential in the next few decades, that really excites me.
Thank you, panelists. Right. Let's see here. Okay. Jeffrey Kassoff says, I recall the Viking mission to Mars in the mid-1970s had some false positive results. Will protocols be developed to limit the debate from contrary findings from different assays?
Well, again, we have the good Dr. Treeman here, so he can correct me if or fill in the gaps where I missed stuff. It's not that they were necessarily false positives, it's that the detections were ambiguous. So we didn't know because we had disagreement between the different instruments. So we had one instrument saying, yep, we found something, and another instrument saying, no, we can't find anything. So we got an ambiguous result. And in a way, we didn't know how to look for life. We didn't really understand what life was. We assumed life as we know it as humans and what we see in petri dishes from from high school biology. We really didn't have a full breadth of understanding of our microbial world and the extent of extreme environments. We didn't have an understanding of any of that. So, we've made significant advances since Viking. And so, yeah, our next round of instruments, it's going to be a requirement of a lot of mutually confirming tests, and ultimately it may just take sample return to come back here for us to fully confirm whether or not we have found life. And even if we bring a sample back here, it won't be any one test. It'll be a team effort across the entire community to look at these samples from a whole different bunch of perspectives and bunch of different instrumentation, different analytical methods, and they're all going to have to agree somehow for us to be able to confirm that what we have is life.
Thank you, Kennda. Okay, next question from our audience. Scrolling back up. Okay. What is the general thinking developing as non-carbon based? Right, our panelists are thinking about this question, so give us a second.
Okay, I'll try to take a crack at it. The reason we like carbon is because carbon forms really stable polymers that, like a very, very closely related silicon can't. So I can't say with complete certainty, of course, but life as we know it uses a lot of polymeric material, and it's really hard to think of another element who would do the same thing, if that makes any sense.
All right, there you have it from our prebiotic chemist expert, and therefore it's the word of law. Okay, so the next question we have here is from, yep, I asked that. Okay, which observatories, current and future, are most important for determining the habitability of exoplanets?
In 1993, we detected the first exoplanet from the Arecibo Observatory. And that planet was very particular because it was orbiting a pulsar star. So that's a very extreme form of star. So it's an irradiated planet. But from the 2010, we have been detecting planets. Since 2010, we have been detecting small Earth-sized planet at the right distance from the star to possibly have liquid water in their surface. So far we have detected many planets like that, but we are shifting now from detecting planet to actually see more information on the planet. We only know their size and their orbit, and now we are moving to check their atmospheres, just to see if they have oxygen and other gases relevant for life or even water. And space missions that are especially appropriate for that is the upcoming James Webb Space Telescope. That telescope has the capability to detect the atmosphere of those planets. We are able now to other telescopes to see the atmosphere or other planets, but usually they are larger than Earth. But the James Webb Space Telescope from 2010 and beyond, 2020 and beyond, we have the capability to sample the atmosphere of those most interesting planets.
So I agree with all that, and I would add that, of course, the TESS mission, the Transiting Exoplanet Survey Satellite, was launched last year, and the discoveries are coming in fast. So indeed, the frontier is on characterizing atmospheres. I think there will be exciting targets that will come out of Webb, but much of what we've discussed at this meeting are next generation telescopes that are just in the developmental phase. And a real advantage of those is that they'll be optimized, they'll be almost sole purposed for characterizing atmospheres. And the discussion now is really what bandwidth to cover between the UV and to the visible to the infrared. And everyone has their favorite gas or combination of gases and favorite wavelengths for those particular gases. And so the discussion is really about optimizing those telescopes so that we can get the most bang for the buck.
Thank you. All right, moving on to the next question. Okay, keeping on with the topic of exoplanets, in your opinion, dear panelists, at what point will the failure to detect biosignatures on quote-unquote habitable exoplanets, when do you think that will deflate interest in astrobiology?
When you start in the field of astrobiology, you are more naive, thinking that using the Earth as an example, this is a planet that has life. There should be many planets with life. But the more you learn about chemistry, biology, you understand that life is very special, very difficult conditions. It's not only from the point of biology, it's also from the evolution, the stability of their planet through time, to have the right conditions to keep that life together for a long time. So now I am more interested not in habitable planet, but habitable conditions without life. That, I think that will be surprising, because we have an example of Earth that we know is habitable and has life. For me, it's more surprising to find something that we can consider habitable, but then we don't find life at all. That's something that we have never seen before. And I think now, this moment, that tells a lot of our origins and what are the possibilities elsewhere. So any answer, positive or negative, is a good answer.
All right, thank you very much, Abel Méndez. Okay, so the next question we have on here is, okay, if you could go anywhere you want on Mars, anywhere, where would you go to search for past or even extant life? I know Kennda has many, many opinions on this.
Yeah, so I've got a couple of my favorite sites that this is Kennda Lynch, LPI, by the way, where I would go to look for both extinct and extant life, and as the good Dr. Lyon mentioned, Jezero Crater is where we're taking our next Mars rover, the 2020 rover, and I am definitely a fan of that, and actually participated in the selection of that site to go look for at least extinct life in the what they're calling the marginal carbonates, what we think could be stromatolites on the lake edge of Jezero Crater, because there was a giant lake in Jezero Crater at one point. And I'm also interested in looking at the bottom set deposits underneath the delta, at the front of the delta, the most furthest deposits from the delta, the river entrance that form the delta that's in Jezero Crater, and look for signs of extinct life there. For extant life, anywhere we can get into the subsurface, I want to go look for extant life. And I think we have a good possibility for looking for both extinct and extant life in Columbus Crater. It's an amazing, diverse environment. Unfortunately, though, because of where it's located, we're going to have to send humans there. We can't land a robot there. The altitude is too high up. A robot will crash. So we're going to have to wait for humans to go there. But I think that would be a neat environment to go look for both extinct and extant life. What did we miss? I think Columbus Crater is a good place to go to look for both extinct and extant life. So those are kind of my biases. But if we can get a drill into the subsurface, it'd be game on. There'd be so much fun things we could look for.
Hi, this is Justin from the LPI. So one of the places that excites me the most is actually going back to where Spirit was and looking at the silica centers, looking at the evidence for hydrothermal activity in that area. I'm a bit biased because I work on hydrothermal activity on the Earth, but life takes hold in hydrothermal systems. There's heat, there's nutrients, and so that would be a great place to go. If we're looking for extant life, I agree with Kennda, let's get a drill. One of my colleagues has proposed a cryosphere deep in Mars that's frozen, and if we can get down and find a cryosphere, especially cryosphere regolith interaction, that would be a great place to go look. I'm going to pass it to Alan.
Yeah. Hi, I just want to toss in my 2 cents here. Another really interesting place would be some of the mud volcanoes on the northern plains of Mars. And those are, places where liquid mud came up to the surface and spewed out. And as such, you're looking at an environment that looks like it had water, it was subsurface, and now it's plopped onto the surface. So that might be an easy way to look at a potentially habitable environment.
All right, so while you have questions, please definitely put them in the chat, and I will ask our panel here. Again, our themes are origins of life, habitability, and searching for life beyond Earth. But while you all type your questions in, I'm going to ask Irena a question. So, what is our current best idea on how life started on Earth?
There's no question about it. Life started with some sort of primitive chemical system capable of Darwinian evolution. And by that I mean it's a system that can select for some sort of chemistry. It can replicate itself, but it can also replicate itself with mistakes. So evolution can happen. And of course, it's easier said than done. We haven't demonstrated yet any other chemical system capable of Darwinian evolution other than our life. So a lot of people in my field studying origins of life are very much guided by our life, and it's probably a very good guess because it's the only example of life we know of. But what I'm thinking about, it's quite difficult to deconstruct our life and to get to the origins, because our life have been evolving, changing beyond recognition. It's almost as if somebody asked you to, gave you a state-of-the-art TV set, smart TV, HD, and without giving you any other information, ask you to figure out the origin of this technology. And I bet you would never get to cathode tube TV. It's the same way you're probably studying our life and deconstructed it. You might never get to our life. The way I'm trying to study it right now is by modeling in the lab, trying to create this type of chemical system capable of Darwinian evolution. And I think this is where frontier of origin of life science is.
Thank you very much, Irena. All right, so again, those of you joining us, please put in your questions. We have about 15 minutes left of this virtual panel. I'm going to ask you another question while you all tippity type. So keeping up with this idea of where life started on Earth, how it started on Earth, Tim, my question for you is, what is the role of impacts on the origins of life? Is it always going to destroy it? Is it actually going to help out?
So the impact of impacts, we've been talking about that a lot over the past few days. And I think a lot of people in the general community come at this at the idea of impacts as being agents of demise, thinking most famously of the one 60-some million years ago at the Cretaceous-Tertiary boundary that led to the death of the dinosaurs, etc. But a theme that's run through many of the talks here is the idea that we might have required impacts to have started it all and to also drive evolution through time. And so there are a number of different things that could be talked about. One is the idea of the delivery of light elements, which tend to concentrate during solar system formation in the outer reaches beyond something we call the snow line, the outer reaches of the solar system. And there's a popular idea now that the large impact within the first 100 million years of Earth may have brought light elements like carbon, a fundamental building block of life, from the outer solar system and delivered it to Earth. We've also talked about hydrothermal. We've also talked about hydrothermal processes, the melting of rock and the generation of high temperature water, which is these kinds of systems that are at the heart of many popular ideas for the origins of life. There was long this view that around 3.8 to 4.1 billion years ago, there was a resurgence in the frequency and magnitude of impacts that might have been sterilizing. That no longer is a popular idea. And while there may have been a pulse, there's no reason to imagine that the life that began before couldn't have persisted through that. We've talked about topography and greenhouse gases. Final thought, we've talked about the possibility of land masses above the sea that could have related to impacts that would have favored these wet-dry cycles. We've talked about preferential or an exacerbated release of greenhouse gases that would have been important in the face of a very dim sun early in our history to keep the liquid water present. And so impacts are, I think, maybe a central part of the conversation here, and mostly in a favorable way.
Thank you so much, Tim. So we do now have a question from our audience. This question comes from John Martinez. I'm going to read this off. I suppose we're ultimately most interested in life that can advance into high technology and not simply develop and then disappear because the planetary geologic processes did not promote long-term development. Have we placed any requirements on the geologic processes that probably need to be present for long-term evolution of life, for example, plate tectonics or having a natural large satellite?
So this is Kennda Lynch, LPI. I would say that is an excellent question that I don't know if we as a community know the answer to yet. I think it's something that we're trying to understand as far as the evolution of complex life. I don't know if we know the full answer to I think we have some answers, but I don't think we have a full, complete answer. And I'll let Tim jump in on that.
And that's a really great question, and I'll keep the response brief. I would say that from my perspective of searching for life on exoplanets, it's actually not about advanced life. And we just published a paper recently where we published a paper recently where we looked in detail at the greenhouse gas compositions that have historically fed into the understanding of the habitable zone. And in fact, without going into details, carbon monoxide and CO2 levels would have been too high or would be too high in most of the as currently defined portions of the habitable zone for complex life, in particular animals. I care a lot about the emergence of animals on our own planet. And a central driver, in my opinion, of that is the emergence of oxygen in our atmosphere and at critical concentrations that persisted. And so a big part of what my research group does is use geochemical proxies to understand the history of oxygen in the atmosphere and surface ocean. And there is a clear correspondence between those events as recorded in the chemistry and when animals appear. And there now is a great debate, including a meeting in London as we speak, about what that cause and effect relationship is.
Thank you so much. I would also like to answer.
Let me add to that. In terms of complex life, we can assume that for planet to have complex life, like animals and plants, that's a very energetic reaction. So we expect the planet to have oxygen for that to happen. But if you mention also technology, I think that oxygen is again necessary for technology because you need fire to melt metals to construct better technology. Otherwise, if you imagine, I'm trying to imagine a planet with intelligent life that try to build tools without oxygen to create tools of metal, their ships won't be of wood and stone. So that's a very limited factors between energetics and the building of advanced technology.
Thank you, Abel. Okay, so we have another question from the audience here. What do you feel are the best analog environments on Earth for the earliest, most habitable periods on Mars and for present-day Mars?
So since I presented research on this week, I will go with sort of my field side of high temperature magma. So high temperature lavas interacting with either water-rich sediments or sulfur-rich sediments, or preferably water and sulfur-rich sediments, producing hydrothermal activity. So for me, the most likely case is these high temperature hydrothermal systems with lots of nutrients, sulfur, iron, things like that for life to take hold.
So for me, this is Kennda. I agree with Justin, absolutely, that hydrothermal systems are definitely probably one of the most obvious, most logical places for life to take hold. But I kind of see it, I don't know, I kind of see it as not a either or. I kind of see it as, you know, when Mars was warm and wet in its early time, we had all these environments. We had the hydrothermal systems, we had lakes, we had subsurface groundwater, and I think any one of those environments are viable for looking for some of the Mars's earliest life. We could have had, you know, we could have had life start in the subsurface with the early hydrothermal groundwater circulation, and then kind of continue on in the surface. So I think it's not just any one environment. I think it could be, you know, there could have been multiple starts and stops, I guess is what I'm saying.
All right, thank you very much. Next question from our audience. So for those of you who are in the audience and did not know, There was a field trip that preceded this conference. We went to Yellowstone National Park. We got to go through different features there, understand them as an analog for life in extreme environments. And so the question from the audience comes from this, and that is, did that Yellowstone field trip on Sunday have any influence on the discussions that happened throughout the conference?
This is Kennda again. Well, I was one of the field trip leaders. I'm going to say, I think a little bit. We had some people often mention in their talks about when they were talking about their analog environment or their process, we had them, mention, oh, and we saw something similar to this in Yellowstone. So I do think that it had an impact, even though Yellowstone is not an exact analog for any of the planets that we're looking at. It gives people an idea of what these kind of system looks like. It gives them something tangible to kind of help them think about what could be happening on their particular planet or on an exoplanet or whatever. So yeah, I think it had an impact in helping people kind of visualize a little bit more about understanding at least hydrothermal systems. Justin.
Just to add to that, there was actually two people who gave talks with images that they had taken on the field trip.
Yeah, that's right.
And so to me, yes, it was directly tied into the meeting when all of a sudden Steve Ruff got up there and showed a picture that he had taken, and then showed a picture of something similar on Mars, and then something similar at Rio Tinto in Chile, and showing that all of these are habitable environments and they produce very similar structures, and that's what we should be studying.
So for me, it was amazing to see the geysers up and close, because as a prebiotic chemist, I talk a lot and study wet-dry cycles a lot. And here I got to see them in action and imagine the system that could have contributed to this wetting and drying. That was quite impactful.
So I wasn't on the trip, but one of the things that I would imagine was discussed, and this isn't my idea, it's really, I think, attributable to Everett Schock, and that is that when you go to these systems in Yellowstone and you go across scales of just something like a few meters, you capture gradients in ecology that may reflect the whole history of life on our planet. And so you can include hydrothermal systems that may have given birth to life, and then you pass through anoxic waters, which is really most of the history of our ocean, and then transitional waters where oxygen starts to appear at low levels, and then fully oxic systems. And in Yellowstone, there's this wonderful banding of ecology that really represents time in many respects as well.
Thank you so much. Yeah, as an attendee to that field trip, I have to say it was my first time in Yellowstone, and I left completely in awe. That is an amazing place. Those of you online, if you ever get the chance, please, please, please go. It was so cool. Even when it was raining the entire day and ridiculously cold, and I'm from Puerto Rico and I don't handle anything below like 80 degrees, and I was frigid, but still, it was really awesome. So the next question that we have, and by the way, we have only 6 minutes left in this virtual panel. So if those of you online, if you have any last questions, please post them. So the next question we have is from John Martinez. Is microbial life sufficient to enable life detection in exoplanet atmospheric spectra?
There's an exoplanet end of the table here. I would say, not only is it adequate and possible, that's what we want, right? I mean, so it's the ability of life to change the composition of the atmosphere. And so on our planet, O2 is a product of biology, including a lot of microbial biology. That doesn't mean that O2 on every planet will be a signature of life. It doesn't, so what I said is that it doesn't mean that O2 on every planet, and we will find it, I'm sure, is a signature of life. But really, one way of looking at this is if you think of our own planetary history, complex life that is able to generate technosignatures that we might see, a tiny fraction. We are a microbial world. Most of what you would be detecting if you were looking at Earth over our history would be microbial. And these gases, whether they're methane or nitrogen compounds or oxygen, accumulate in massive amounts that can be detectable. And my team has been studying through Earth history when those gases would or would not have been seen as a function of the complex ecology that evolved in the ocean.
Okay. I thought Abel was going to answer something, but I guess not.
Well, I
let me
can
look
say
back.
something to add to that. People, yes, people usually think that if we detect oxygen that is related to life, we know other abiotic processes that can accumulate oxygen in atmosphere. You might think that oxygen only means that there is some photosynthetic life like plants producing that oxygen, but we can compare how photosynthesis works. It works at the complex life with plants, but it works also at the microbial level. And the oxygen in our planet, about half of the oxygen produced is produced by cyanobacteria in the ocean, and other half about in the plants in the land area. So there are contribution of different life forms on all scale to the oxygen accumulation of our planet.
Let me just add to that. I give, like everyone here, I give a lot of public talks. And one of the questions I ask of the audience is, in 5 years or 10 years or 30 years, when you see a headline that says methane in the atmosphere of planet X, that methane in the planet, detected in the atmosphere of planet X is within 90% certainty related to life. Will that excite you? Or are you more excited about the sense of intelligent life? And without exception, people jump up and down and say yes, because I think once that they will be excited, because I think once course or a similar course that our planet has.
All right, thank you very much. Yes, the audio did cut out there for a bit. Again, we're on hotel Wi-Fi here, so I'm very sorry for that. Seeing that we only have 2 minutes left for this panel, I'm going to ask the last question, and that last question is, what are the remaining big questions that we are taking away from this conference? What is something that we all need to go home and think about and go and do science to figure it out? In fact, actually, somebody came up here and said the whole chirality. How did that evolve? That was a big one. So I know, Irena, if you want to mention that at all. But yeah, any big questions, take-home questions?
Well, not to sound like a broken record, because it's something I've been talking about for weeks. I think that there was kind of a little bit more realization of the big question of starting to think about other planets as prebiotic planets, like thinking about like what would it take for life to arise on these other planets. And I think that that became more a big takeaway from my perspective.
So this is Justin. The big takeaway from me is, how do we definitively detect life on another planet? We're still not there yet. We're still all working at it from different directions. This was a great meeting, bringing together exoplanet people, microbiologists, early Earth chemists, geologists, geochemists, geobiologists, and starting to have that conversation, but we're all not on the same page. We don't all use the same language, and we need to get there. And that, to me, I'm still shocked at how much we still have to do and how much we have to work together to get there.
I would like to develop a framework to detect universal life. Of course, we have only one example right now, and life might look very different elsewhere in the universe. So what are the universal principles of life? And so if we can define something like that, it would really help us detect life that's different from ours elsewhere.
My interest is that we should have a better reconstruction of the evolution of our planet and life through history. That's something that is very necessary to understand. If we ever dare to try to look life elsewhere, the first thing that you have to know to understand is your own biology. You are not being Earth-centric. You are establishing the baseline for any detection just to say, is that related or not to our planet? So that requires a lot of understanding our evolution, our planet.
I would say consistent with what we've done over the past few days, and really a life lesson I've had over recent years, is that I have a background that's very much based on observation. Initially, it would have been in the field, things I saw with my eyes. Increasingly, it became measurements that required instruments, geochemical measurements. And through those measurements, we've come up with a history of the evolving environments, and we can map the evolution of life on top of that. But really, for me, where the forefront is, and the things that I'm learning most about now, are numerical approaches. It's taking these essential building blocks of a planetary system that are required to generate and sustain life, and mixing them up in all sorts of wonderful ways that you can only do computationally. And so a lot of the forefront in exoplanet research is an informed use of models of oceans and the photochemistry of atmospheres and the predicted spectra and the detectability of those spectra. And I think that theme runs through a lot of the work here.
And with that, I want to thank the panel once again for joining us. And thank you, audience members, for joining us today and asking all of your great questions. We, like Andy mentioned on the chat, we are hoping to continue doing these type of webinars at the end of USRA LPI conferences. So signing off from Big Sky, Montana, thank you, everybody, and may the force be with you.